Alright, hello YouTube. I'm not dead. Yay. I just recently got my filming setup redone here, so this will be the first video I've done in quite a while. And I wasn't even planning on doing a video today, but I was putting together a little circuit here for class today. The instructor wanted me to do a little demonstration on Zener diodes. So I threw together a little circuit here to show my classmates what a Zener diode looks like. And I'll actually be sharing this video with my classmates after I publish it. So hello classmates, if you're watching this. So I haven't done a video on the channel yet covering Zener diodes yet. So I'll get to that in a little bit later in the future. But I just figured I'd quickly explain the circuit that I've got set up here, and a little bit about Zener diodes. And a little bit, actually we'll have to start talking about what a diode actually is. And so we're going to look at the electrical symbol here for a diode, which is this funny little arrow with a line, and then you go that. Now this is a really important component in electronics because it only allows electricity to flow through it in one direction. So when you're looking at conventional current flow, with this being the positive side and this being the negative side, current can only flow through this device in that direction. If you try to put current in the opposite direction, it acts like a locked door. So this has a number of applications. The most common one that comes to mind is in a battery charger. You'll put one of these in line with the battery so that when the battery is fully charged or you unplug the charger, the battery doesn't start to discharge back into the charging circuitry. It's also used to prevent inductive kickback in larger motors, and a number of other things. Actually, your cell phones, your cameras, your TVs, none of those would exist without these diodes. If you take two diodes and you slap them end to end, you end up with something that's called a transistor, and we'll get into more detail in later videos. Now, with a standard diode, they can only stand a certain amount of voltage in the reverse bias direction if you're trying to push electricity through it in the wrong direction. And at a certain point, which is called the peak inverse repetitive voltage, the diode breaks down. It lets out a little curl of the mysterious blue smoke that all electronics run on, and it dies. Now that's a pretty substantial voltage. This little tiny component here, this is a 1N4007 power diode. It can handle 1,000 volts in the reverse bias direction. That's just this little tiny thing here. So the amount of voltage these can block in the reverse direction is actually pretty substantial. But then you can do something a little neat with a different component called a Zener diode, and that's what these little reddish guys here are called. Now the symbol for that one looks a little like this. It's the same as your standard diode symbol, but instead it's got this sort of little zigzaggy line instead of the straight line of the previous diode. Now these are really cool because, like a standard diode, in the forward biased direction they drop 0.7 volts and then allow current to pass through them. But if you put them in a reverse bias, they have a voltage rating at which they break down, and then current begins to flow in the reverse bias direction. But this doesn't actually kill the diode. The diode survives this, and it's supposed to survive it because you can use a Zener diode to regulate voltage. One of the more common ones for that would be to cut out the current in a circuit when a battery drops to a certain voltage. So I'll quickly sketch out a quick and dirty circuit to show you a little bit about how that works. just throw the Zener diode right there. We'll do this, and then we'll do this, and this is going to be that. And then we're going to have our battery here. So let's say this is just going to be our load here, and that could be a light bulb or a motor or any number of anything that needs electrical current. And then we've got a stabilizing resistor here. This is kind of important. I'll get into that in a minute. And let's say this is a 12-volt Zener diode. It's in the reverse bias direction. So we've got the positive terminal of the battery here and the negative terminal of the battery there. This is called a stabilizing resistor. And so let's say this is a 16-volt battery. Now, when this Zener diode begins conducting electricity, it only conducts 12 volts. That's all that goes through there, never more, never less. So with it in parallel with the load here, the load is going to see 12 volts when that Zener diode is in breakdown, despite the fact that the battery itself is 16 volts. And the way you get away with it is the stabilizing resistor is going to dissipate the current from that remaining voltage. So if this is 12 volts, this stabilizing resistor here is going to be dissipating 4 volts. And as batteries discharge, their voltage begins to drop. So this is going to drop down to 15 volts, then 14 volts, then 13, etc., etc. And as the voltage of the battery drops, the voltage on the stabilizing resistor begins to drop, but the voltage in the Zener diode remains constant. And then when you hit that critical point at 11.9 volts, that Zener diode stops conducting and the load stops seeing voltage, and then the circuit cuts itself out. It's very quick and dirty. You get some leakage current. You don't want to do anything sensitive with this, but that's a very simple voltage regulator circuit using a Zener diode. Now this here is just it's a very impractical circuit. You won't see anything like this in real life, but what I've set up here is basically a little bit of a voltmeter using Zener diodes of various different voltages. So I've got a 3.3, a 3.9, a 4.7, a 5.1, a 5.6, and a 6.2 volt Zener diode all in a row here, connected in series with some blue LEDs and a couple of 470 ohm current limiting resistors here to keep the LEDs from exploding. And then over here I've just got a quick and dirty voltage regulator circuit using an LM317, and I'll explain those in later videos as well. But suffice it to say, I can feed a static voltage into this, and using this potentiometer it will output a regulated voltage. So I don't actually at the moment have a power supply that's capable of firing this circuit up properly, and I'll actually be setting up a Patreon link in the description below to start up funding to get myself a proper current controlled power supply. So I'll put that link in the description, or maybe I'll put an annotation over here somewhere. But I can sort of show you how the circuit works with the little 9-volt battery here. So all of the math and components here are set up for running off of 12 volts. So we won't get a full demonstration of the circuit running, but we'll get something close. So there, I've connected power into that now, and right now the standby voltage of the LM317 is 1.25 to 1.5 volts, which isn't enough to cause breakdown on this first Zener diode, because that Zener isn't going to break down until 3.3 volts. So we're just going to start tweaking this potentiometer up here, and I hope this shows well on camera. So we're just going to start turning it up, and you see the LED starts to light up there. And that's when we've hit that, or are getting close to that 3.3 volt breakdown voltage. And then as I continue increasing the voltage, you'll see the LEDs light up in a row there as each Zener diode reaches its breakdown and starts conducting current through those LEDs. Now if I was able to feed 12 volts into this voltage regulator, we'd see all of these LEDs lighting up, but I don't have enough voltage currently to feed the circuit. So that's just a quick practical demonstration just to explore the science of how the Zener diodes function there. And I'll be taking this into class later to show my classmates the little practical demonstration in person there. Now, just for the fun of it, I'm going to quickly sketch out what this circuit looks like in case anybody else wants to build this circuit for themselves and explore the science of Zener diodes. So it's very simple. I'm just going to draw a couple of rails here. What we've got is we've got our 470 ohm current limiting resistor there. That can be pretty much any value, just as long as it, for the maximum voltage that you'll be putting through the circuit, you can use an equation that I've talked about in a previous video to determine how to make these LEDs not blow up from the current you're putting through them. And the next component in line there is going to be our little Zener diode here. So we'll do the weird zigzaggy line there, and then our arrow. And this is, of course, in the reversed bias direction. So this is actually the negative side of the diode that's facing into the positive side of the circuit, which with any other diode you don't want to do that because you'll ruin it. But with the Zener diodes, that's actually how they're used. And then we've got that in line with a light-emitting diode, which is your standard diode symbol there with the arrow and the line, and then we just add a couple of lightning bolts here to demonstrate that there's light coming out of it. And then that goes over here to the negative rail. And that, of course, repeats itself a couple of times, like so. And we'll just, I'm not going to sketch out all 6 of them, but that's the basic circuit, and then it just goes down and down. And you can use as many Zener diodes, as many LEDs as you want, just as long as you get the calculations for the voltage correctly there. And then that's coming into my little LM317 here. This is the V out pin. This is the voltage adjust pin here. And then this is the voltage in pin. These are magical little devices here that you can use to regulate voltage out of a circuit. So the way you set up a voltage regulator like the 317 is just like this. So off of the adjust pin is basically the LM317 reads the resistance set up on the adjust pin and regulates the outgoing voltage appropriately. Now in this case what we've got, oops, I forgot a part here, because that's a potentiometer, so it's set up like that. So we've got a 200 ohms worth of resistor set up like so. And then we've got a 0 to 1 k ohm potentiometer set up here. And so this these values, there are calculators online that you can use to determine what resistances you need to use for an LM317 to provide a voltage. But when this resistor is at 1 k ohm, it's going to be putting out about 7.5 volts, which is sufficient to fire all of these Zeners. But the LM317 consumes a certain amount of voltage, as well as each of these Zener diodes needs to have its voltage exceeded by a little bit. So basically what I'll be doing at school is I'm going to be feeding it 12 volts to make sure that I get enough voltage coming out of the LM317 to fire all of the LEDs. Now, as you adjust this potentiometer from 1 k ohm down, so that's basically with the wiper all the way over here. At 1 k ohm, it's putting out 7.5 volts. And as you reduce that voltage by moving the wiper in this direction, that voltage drops and drops and drops and drops until you've got the wiper at this end of the resistor, in which case it's only going to be putting out about 1.25. That is a terrible 2. There we go. 1.25 volts, which is the quiescent voltage of the 317. You can't actually go any less than that. That's just a quick, dirty way of controlling the voltage going into the circuit there. Using a potentiometer in this fashion is really wasteful because you're just dumping your current into ground without actually utilizing it, and the potentiometer will actually start getting fairly warm when you do it that way. There are better ways to do this, but like I said, this circuit isn't meant to be practical. We're just exploring the science. So I think I've rambled on long enough with that. With this, so if you liked the video, give me a like or a subscribe and share it with your friends. And I will see you in an upcoming video when I do another kit build. So look forward to that in the next couple of days. Thanks for watching. Bye-bye.